Yes, it is. All right, sweet. I can move this down. Now it's being recorded. So for the tape, I was just mentioning that the midterm is coming up on Monday of next week. I'll talk about it again on Thursday to remind you. And it's essentially, in terms of being cumulative or not, it is in the sense that there's C on it, and I expect you to remember the stuff from earlier in the semester. But there's going to be, of course, an emphasis on things like pointers and stacks and lists and those semantics, because that's what we've been talking about lately. That's top of my mind. So as I'm writing questions, that'll be the first thing I think of. All right, let's go dig back into the stack. So as a reminder, we looked at the heap earlier. And remember, the heap grows from low memory addresses up toward the higher memory addresses, and it grows when we do a malloc. It shrinks when we do a free. So the heap is sort of constantly expanding and contracting as we use memory in our process. The stack, on the other hand, starts at the top of memory, the top of user memory, and grows downward. So the highest address is really the bottom of the stack, and as we move the stack up, we're going to subtract addresses from it. So it grows from large addresses towards smaller addresses as we use the stack. We're going to be talking about this bit today. And just because we're looking at this picture, just a reminder that on 64-bit systems, the first third of memory is for the, well, I guess it's the top. The first 2/3 of memory are for 3/4. The first 3/4, who expects the Spanish Inquisition? The first 3/4 of, geez, there. Is it not shared? Hang on. There we go. Is that being shared now? Can you see it? Thank you. You're welcome. So the first 3/4 of memory are for the user space. That's our running program, the process. And then the top quarter is for the kernel. It ends up looking this way because of the way virtual memory is handled. So this stuff has to be mapped into every process, essentially. We'll talk about virtual memory probably in about a week. But for us, we just have to remember that the stack is at the top and grows down. Heap is at the bottom and grows up. And again, just since we're in here, this stuff down here in the yellow bit, so text is our program. That's the actual code that's going to run. RO data, read-only data, stuff like strings, other immutable stuff. Data is for, this is going to be uninitialized variables and such. So the yellow and purple down here, these pieces come from our file. When we load the file into memory to start executing that program, that's that ELF format that we looked at earlier, executable and linkable format. So those come from the file. And then all the other stuff, these are just memory structures that are set up by the kernel for the running process. And the stack itself, just as a reminder, 3 operators: push, pop, and peek. Push puts something onto the stack, pop removes it. Peek looks at the top of the stack. You can return a reference to it if you want without actually changing the stack. And recall that stacks are just like, I don't have anything stackable. Hang on. I need things that are stackable. So with a stack, we're always working from the top, right? So if I got an empty stack, I push something on the stack, it's at the top now. The next push does like this. If I do a pop, now the thing that was there before is at the top. Another pop, I got an empty stack. Using props is part of the professor training that we go through, just ad hoc props. So it's essentially a LIFO queue, and we only do work at the head. So we don't worry about all the stuff, below that. We're just dealing with the top of the stack all the time. Oh, and speaking of stacks, this came up in A1, so I'll mention it to you guys too. PS4 is coming out. I'll probably release that today. It's out for review with the TFs right now. PS4 has to do with stacks. And specifically, you'll be implementing a reverse Polish notation calculator. RPN is a mathematical expression system that lends itself really, really well to evaluating expressions with stacks, to the point where if you're coding a program up and you're using standard notation, like 5+2 and so on, with all the parentheses and all that stuff with precedence and so on. There's none of that in RPN. And so what computer systems usually do is they'll take that infix notation, 5+2 in parentheses, -4 and so on, and convert it to RPN and then do the calculation, because it's faster to convert and then use stack than it is just to evaluate the expression in place. So RPN is really cool. I'm an engineering geek, so I've used RPN since the 70s, I think. All my calculators, none of my calculators have an equals key on them because I just use reverse correlation notation. I don't need an equals key. In RPN, when you get done evaluating an expression, there's one thing on the stack, and it's always the evaluation of that expression. So the result is always the top of the stack. It's a really, really fun system if you don't know it already. And maybe you'll even decide that you like it so much, you'll go out and buy RPN calculators. I like the HP RPN calculators, like the 16 for programming or the 12 for finance and so on. And you don't need an equals key, and no parentheses either. There's no parentheses. Everything's in order. All right, so PS4 coming out. I haven't seen anything negative from the TF, so I'll probably release that this afternoon. How's the computer calculate without RPN, and why does it take so long? George, I don't think it doesn't do it converts to RPN and then does the calculation. What do you mean it takes so long? Like a couple of nanoseconds is too long these days? What do you mean, George? Why does it take so long? Oh, by not converting to RPN. It's the parentheses. Because parentheses change the order of precedence, you got to scan across the entire expression to figure out where the parens are. And then you got to save off scratch values because you're going to calculate something inside parentheses and put it aside and then use it later. It's fairly complex. But if you just convert the thing to RPN, the rules for conversion are really simple around when you see a paren and what do you do and so on. Use a stack to do the conversion. And once you've converted, you're done, and just you zip through the stack, evaluating the expression. It's very fast. Yeah, so the conversion to RPN is faster than the evaluation inside the infix system, I guess, is why it's faster. This is just a representation of the props that I just used. So empty stack, push a 5, I got a 5 on top. Push a 42, now I got a 42 on top, the 5's below that. Do a pop, the 42 comes off, now I got a 5 at the top, another pop, and I got an empty stack again. Empty stack means that head is null. Ba-da-ding. Oh, I hit my move goal, and it's only 2. A very, very unambitious move goal, clearly. All right, so let's move on. We talked about a lot of this on Thursday. So let's talk about the stack itself. So one thing we're going to use with the stack in terms of the process, using the stack to move stuff around, we're going to use the registers in the CPU pretty heavily. And let me just back up a couple to remind you what the registers look like. So these are the ones on the left are the 64-bit registers. The 32-bit ones are a subset of that. So we've got these 8. And then there's another set of 8, these guys, right? R8 through R15. These are registers that are physically on the CPU itself. They're very, very fast. These are the things we're going to use in terms of the stack and processes talking to each other. So these are all going to come up. And I apologize, as I was writing this, I realized as we were going through the A1 lecture, I kept bouncing back and forth between 32-bit and 64-bit names. I think I caught them all. As we were talking, I think I caught them all and corrected them. So I'll repost the PDF so that they're consistent for you. All right, cool. So what about that stack? So the most common thing that's going to happen is that we're going to be in some code and then do a function call. The thing about making a function call, it just seems like a normal thing when we're writing C code, right? Because, oh, blah, 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 function, maybe some results coming back. So a equals add 1 is a function call. It's going to go jump off and do that function and then return my result to me. Well, those functions are not connected to each other in any way. They're just a bunch of code. Each function is code sitting in memory somewhere. Like there's nothing connecting it to anything calling it or anything like after it. It's just sitting there in memory. And so we need some way to get information into the function, like its parameters. We need some way to get stuff out of the function, so its return result, the return value, but do it in such a way that like it doesn't have to know who called it, because it doesn't really know who called it. It's just all of a sudden we start executing instructions. Because if you think about it, a function in memory, like the address of a function, it's the address of the first instruction of that function in memory. And these things get relocated. So like, where's the function live in memory when we're running? I don't know. Who knows? Could be anywhere. So we got to go find it. There's a calling convention that takes care of a bunch of this stuff for us. It's called the System 5 Application Binary Interface, the ABI. So the ABI is a big document, huge honking document. It's got a bunch of addendums. So as we moved from 8 to 16 to 32 to 64-bit machines, they just issued addendums to the spec. The ABI came out in, the 70s maybe? When was System 5? My System 5 was mid-70s, I think. Anyway, so it's a really old spec, but like this is the way that programs run and have run since then, and probably before then. They were probably just codifying stuff that was already happening. It hasn't changed over the decades, I guess is what I'm saying. It has changed in terms of like the number of registers. So an 8-bit machine only had a couple of registers. A 64-bit machine has tons of registers. And so the way we use the registers changed slightly between the architectures just because we had more of them. So that's the ABI. I mentioned here, and clearly it happened to me too, a lot of times you'll be reading stuff like articles or books or something, and they'll bounce back and forth between EAX and RAX, for example. EAX is the 32-bit accumulator, RAX is the 64-bit accumulator. You just have to remember that really it's the AX part that you're looking at. It used to just be AX, and then it was the EAX, the extended AX, and then they had to change it again for 64-bit machines to RAX. They're all AX registers. It's all an accumulator register. And just a couple of words that I'm going to consistently use here, or try to consistently use: caller and callee. The caller is the thing that calls a function. So I've got some code running, it calls a function, that's the caller. The callee is the thing that's being called, typically the function in this discussion. All righty, we're going to use stack frames to do this. I guess I could make this bigger, huh? We're going to use stack frames to manage this. So a stack frame is essentially just a portion of the stack. We're going to make space on the stack for several things. One of them is anything I need to save off. Like if I need to save, like it's almost like a scratch space. If I need to save some value and use it later, I'm going to use the stack frame space to do that. If I need to do some calculations, like move stuff around in memory and throw it in registers and add or subtract or whatever, I'm going to use the stack frame space to hold those variables for me. It really is just scratch memory. The problem that we've got is that a function can call a function, can call a function, can call a function. Like if you think of main is a function, right? Any function that you call outside of main is the caller, and then some function is the callee. Well, as that callee function's running, maybe it calls a function, and now it's the caller, and the thing it called is the callee. So I'm going to end up with all these stack frames sort of built on top of each other. Each one of them represents the state of the caller at that moment in time. It's actually an astoundingly useful thing, especially when we're debugging I showed this in A1. I didn't happen to have C line up. We were doing JavaScript in 4.11. And so we are over here in JavaScript. Let me just run this thing. So I got a debugger attached to this. And I'm just going to hit, can you just hit 3K? So I'm just running a debugger in here. Over here, though, over here, see where it says frames? These are all the stack frames that were generated, in this case by JavaScript as it was running. The top frame is the place we currently are at. So here we stopped inside this, there's a function here. It's hard to see, that's the function call right there. And all it does is set a variable, but that's that spot. So in that stack frame, this is inside that function. The function that called this one, this is its frame. The function that called that one, this is its frame, and so on. And you'll notice that the variables over here, some of them are similar, some are not, but they're all unique values, right? So these values belong to that frame, to the caller in each case. Those values are saved so that as I unwind this, like here, I'm up at this, like this line of code. When this function exits, this stack frame goes away, and now I'm back to this stack frame, and it just continues where it left off. So the stack frame is a way to take a snapshot of what's happening in the process just prior to the function call, save it, go run the function in a different stack frame. Then when I return, I can return to that original stack frame and have all my stuff, basically. It looks the same in C, roughly the same, which is why, since I had this running, that's what we used. So that's a stack frame. Now, just a quick caveat, the stack frames are not created by the compiler if we don't ask it to do so. We ask it with the -G flag, the debug flag in GCC. Anytime we're building an executable or a library that has debug symbols associated with it, it's also going to use stack frames to do all the stuff we're talking about. If I leave the -G flag off, so I'm not debugging, the compiler is going to optimize this for me. And one way to optimize it is to not use stack frames, because stack frames can be a little bit slow. I've got to set stuff up in memory. I got to move pointers around. It can be a little bit slow. There are ways to use the CPU's registers to do exactly the same thing. They are just worlds faster than manipulating memory in the stack frame. So the compiler is going to optimize out the stack frames essentially. For us, like, we're almost always going to be doing debug code, so we'll have stack frames to work with. They're extremely useful, like being able to look into a stack frame 3 calls deep, see what the values of stuff are, see what they were before. Like, it's a really valuable debugging tool. We use stack frame dumps all the time to figure out what the problem is in code, especially in C, where there's not a lot of hand-holding. For example, I didn't mention this to A1, like PS4, a lot of PS4, like the stack itself in PS4 is really easy. Like, the stacks are just really simple to implement. The trick with PS4 is I'm asking you to do a lot of error checking. C doesn't do any error checking, really. Like in every other language, there's a try catch. Like in Java, it's try catch everything, right? Try, blah, catch, error. There's no exception handling in C. It doesn't even have the concept. So there's no try catch. There's nothing. We have nothing. And so it means that we have to do a lot of error checking in our code to make sure that results are what they should be. That's a lot of what PS4 is about. I don't know why I mentioned that. It just popped into my head. All right, so stack frames. So input parameters. I'm going to call a function like this, and I want to pass some parameters to it. The first 6 arguments are going to be placed into registers. The first 6. So here, arguments 1, 2, 3, 4, 5, 6 will go into registers in the CPU. And they're done in this order: RDI, RSI, RDX, RCX, and then R8 and R9. and they go in left to right order. So the 1 is going to end up in RDI, the 2 will end up in RSI, the 3 in RDX, and so on. The 6 will end up in R9. If I've got more than 6 parameters, now I've got to use the stack. So 7, 8, and 9 over here, those are going to end up on the stack, and they're pushed in reverse order. So I would push them 9, 8, 7. Why do I push them in reverse order? Because it's philo, it's a stack. So if I push 9, 8, 7, what's sitting on top of the stack? The 7. If I pop it, the next thing up is the 8. Pop that, the next thing up is a 9. So if I push them in reverse order, when I enter the function, I can pop the stack and they'll be in the correct order to fill in the parameter list. That's only true for 64-bit architectures. 32-bit machines still use the stack. They just use the stack. 16-bit also. The reasoning is that with the 64-bit architectures, they expanded the number of registers significantly. So I just got a lot more registers to play with. And so it makes sense to use them to pass the parameters because they're faster than hitting memory in the stack frame. So those are the input parameters. This is done by the caller. So when the caller wants to call a function, one of the first things it does is push the parameters if it needs to, or throw them into the correct registers. The next thing it does is, it pushes the return address. So I'm going to have the return address on the stack in front of the input parameters. And it's there so that when I'm done with the callee function is finished with its work, it needs to know where to go back to. Like, where's it going to jump back to? Who was the caller? We just store the caller's address in the frame so that when I'm done, I can go back to the frame, say, oh, that was the address I came from, and then just jump right back there. You'll see it coming up in a picture. All right, so I'm going to enter a function. So this is just after the function call. Nothing else has happened. On entry, the very first thing it does is it has to preserve these 7 registers. This is part of the ABI. So the application binary interface says the callee must preserve these 7 registers on a 64-bit machine: RBX, RSP, RBP, and R12 through R15. If you're not going to use those registers, you don't have to touch them because they're not going to change. If there's a value in RBX, for example, it's just sitting there. I do all my work over here and then I return. It hasn't changed. I don't need to do anything to like preserve it. I preserved it by not using the register, so I don't have to worry about that. So preserve these 7 registers if necessary. And I often get questions like, well, how do I know if it's necessary? The thing in assembler is there's no abstractions going on. Like, you're writing what essentially is binary code for the CPU, just one level above that. You just look at it and you say, am I touching RBX? No, I'm not. I don't need to preserve it. Like, you know whether you're touching it or not. There's no guessing. There's no abstraction. It's just exactly what you tell it to do. So because you have complete control over the assembly language when you're writing it, like, there's no guessing, right? The next thing we do is save the base pointer. So the base pointer is currently, when I make the function call, that base pointer, the value in RBP, is pointing to the caller's frame. When I return out of the function call, I need to restore that so that the caller can see its original frame. It's a stack, right? So as I make calls, these stack frames are just going to stack one on top of each other. When I pop this one off, I want to make sure the caller sees its original stack frame. So I need to store the pointer to that. There's a lovely picture coming up in one slide, I believe. So I'm going to save the base pointer, and then I'm going to set the stack pointer equal to the base pointer. Actually, the base pointer equal to the stack pointer. It essentially gives me a new frame for the callee. It looks like this. So this is just prior to the function call. This is the caller up here. So this is the original function, and then it's going to make a call into the callee. Well, the caller has a frame. It's pointed to by this RBP value. That's the base pointer for the caller's frame. When I call this function, I need to save that value, because when I get out of this function, I need to make it look like just blue. The green part is for the callee. When I come back out, I'm back to the blue part, and I need to make sure that pointer is pointing back to where the caller expects its frame to be. It's actually going to look like this. BIP. So, and by the way, the stack, I went back one. So the stack pointer, that was the base pointer for the frame. As I pushed stuff onto that stack frame, as I do pushes, the stack pointer moves up on each push. And so if I started at the base, these are going to be equal to start. As I push these things on, the stack pointer moves up. It's always pointing to the top of the stack, essentially. Oh, sorry, question with Jonas. What if the callee becomes a caller? Wasn't that a Sting song? Same thing. There would be a chunk up here that was the original, like this guy, or this guy. We'd have them down here, right? So we'd have another frame with RBP and RSP looking like this, just be another frame on top of that one. And it can go pretty deep. You've got a lot of frame space. Does it have its own version of RBP? No. Jonas, that's a really important point. There's one RBP. There's one RSP in the CPU. These are just CPU registers. There's only one copy of them.
Right.
The program itself, the running process, basically has access to all of them, but each function call, each stack frame is going to manipulate those in some way. If I manipulate something that somebody else is expecting to use, like RBP, that's why I've got to save it and then restore it on the way out. Just basically, it's like, it's like going to a friend's house for the weekend. Like they're away. They said, hey, you can have my house for the weekend. Just, clean up when you leave. So you go in, like maybe you're really like weird about it. Like you take a picture of the place, right? When you walk in the door, so that when you leave, you can put everything back to where it should have been. That's the same sort of idea. And if you're not going to touch something, you don't have to move it, right? So you manually store the prior RBP so you can put it back later. Bingo. You've got it. So this is the call, right? Just prior to the function call, the base pointer is the starting point of the stack frame of the caller. It's pushed arg7 and arg8 onto the stack, and then it pushes its return address onto the stack. So the return address is going to be at the top of the stack, essentially. Now we make the call. Well, the ABI says the very first thing I have to do is preserve those 7 registers. In this particular instance, I'm only going to muck around with RBP. So I don't have to preserve any of the other ones. I don't have to save them. I'm not going to touch them. So how do I preserve it? Just push it. So it was like this. Now I'm into the callee. I just jumped into the callee. The stack pointer still points here. There's only one stack pointer for the whole process. But now I'm going to do a push of RBP. So push RBP, that pushes RBP here, there, there. And a push moves the stack pointer to the new top of the stack. So now the new stack pointer is going to be sitting here. I've saved the old base pointer. So now I can set my base pointer to be the same as the stack pointer. So this line of code moves RBP. It was over here, right? It moves it to here. And now that's the new frame for this function, for the callee. When I get out, when I'm all done here, I'm going to pop RBP back to its original value, and that'll have RBP pointing back to here, and then I'll jump back to the return address, and this green stuff will just essentially go away, and I'll be back to the caller with its blue stack frame with RBP sticking, it's pointing right there. All right, so that's the situation just after preserving any registers that I need and establishing a new frame on the stack for the callee. Now the stack pointer, like we've already seen, the stack pointer is going to move around. When I do a push, the stack pointer moves up. When I do a pop, it moves back down. It's always going to point to the head of the stack. The base pointer, however, does not move. that base pointer just sits there. That's essentially the start of my frame. Anything I need is like accessible here now. Like if I need arg8, all I know, I just go back 4 words, right? So I start at this base pointer, that's my pointer, go back a word, go back a word, go back a word, go back a word, that's where arg8 is. If I need arg7, it's back 3 words right there. So I can go back and refer to them using offsets off of the base pointer. And the offsets, you'll see them coming up. Here they are, in fact. So for example, if this is RBP pointing right here, the return address is this part right there. Remember that? That number in front of this reference is an offset. So that says add 4 bytes to whatever is in RBP. That parentheses is like dereferencing a pointer. It's the value at. So RBP has a pointer to right there, 4 plus that. So larger addresses are on top. So if I add, I'm going that way toward the top of the page. So I add 4 to it, I end up here, right there. So 4 away from RBP is, sure enough, that's the return address. If I want arg7, it's going to be up from there. It's probably going to be at, it's probably 8, isn't it? I think it's 8. It's 8 correct here. I made a note earlier. So I think it's, those are words. I believe it's up. So that's 4 bytes up, that's 8 bytes up, that's 12 bytes up to arg8. So, but I can use these offsets from the base pointer. The base doesn't move, that base pointer just sits there, and I can refer, if I add to it, I go sort of toward this zone of the stack. If I subtract values, I'm going this direction from the base pointer. And it's this space up here that I'm going to use for my scratch. Just temporary values I'm going to write. Where are we? Here we are. Next thing I want to do. So far I've done 2 things. I have preserved RBP, so I pushed the old RBP onto the stack. That way I can pop it back off when I need it. And that's the caller's RBP. So that's the caller stack frame I'm preserving. Now I've set up RBP to point to a new stack frame, essentially at the top of the stack. Oh, it's a long question from Jonas. That makes a lot of sense. We could achieve the same result by doing -4 if we dereference the old location of RBP, the one we saved before the last function call. Yeah, as you said, you wouldn't to get arg8, but you could, because this value, that old RBP, actually still refers to this spot right here, right? And theoretically, that's 4 up from that. There might have been other stuff there, so it might be a little more difficult to calculate. You could probably do it. I wouldn't, but you could probably do that. That's the beauty of assembly language. Like, there's no one to tell you can't do something, It's like you're just moving bits around. Does it make sense to do that? I don't know. Maybe it does, maybe it doesn't. But you can still do it for sure. Like, there are very few errors in assembly language. Divide by 0, segment violation if you try to, get to memory doesn't belong to you. It's like overflows. Actually, overflows aren't even errors. It's just a flag. That's why assembly is so much fun. There's no one telling you, no, you can't do that. All right, so there we are. We preserved RBP. We set up a new stack frame. And now I'm just going to give myself a little bit of space. So that's 20 hex, right? So that's 32. So I'm looking for 32 bytes, 4 words. I'm sorry, 8 bytes, 8 words. Jeez, oh, Pete Bear. It's 32 bytes, which is, there are 4 bytes per word. So that is 8 words, right? I was giving myself some space. So that's RSP, and I'm subtracting 20 from it. Recall that the instruction format is instruction, source, destination, and the destination is overwritten by whatever you do to it. So here I'm subtracting 20 hex from whatever there is in RSP. RSP originally was here, copy that and that. So it was originally here, right? When I subtract 20 from it, subtracting means it's going to be a smaller address. And so it's going to move toward these smaller addresses. I'm just going to say it's right there. It just gives me some space. The reason I do that is if I immediately do, let's say I save some value into that spot and then immediately do a function call, well, what's going to happen when this guy is the caller and the callee starts doing things, right? The callee is going to see the frame ending essentially right there at RSP. So if I didn't move RSP up, if I just did this and then stored some stuff here by doing pushes, not even a push, just actually directly sticking something in memory there, and then did a function call, I'd probably lose those values because there's nothing really identifying them. There's nothing protecting them. If instead I move the stack pointer up, now I've got some space here that's not going to be touched by any callee. 4 bytes, 4 words. I guess it was late at night when I was probably a martini or two into this while I was writing this slide. All right, so that gives me a little bit of space, right? Now I can start mucking around. Like at this point, now I've saved off the registers I have to save. I've set up a frame for the callee, and I've set up some space inside that frame to work with. And again, like typically we're writing the assembly language, so we know how much space we need in the stack. So we just subtract that much space. That's all you need to do. It's like there's no mysteries here. Like we know exactly what these numbers are going to be because we can look at them. Now I'm going to start doing some stuff. So here I'm just going to move a 42 hex into this location. What is that location? So I'm starting at RBP and I've got a -4 offset. So it's 4 bytes below RBP. There's RBP. 4 bytes below it is going down because smaller addresses are down in this image. So subtracting goes down. 4 bytes is right there. So 4 bytes from RBP, I'm sticking a 42 in there. Now maybe I do a couple of pushes, like a push R15 and a pop R15 and so on. If I push R15, what's going to happen to the stack pointer? Oops, just copy you. Copy you, make a little text for you. So if I do a push of R15, it's going to go right here. Well, what's going to happen to the stack pointer? Stack pointer moves up, right? Because a push is going to move the stack pointer. And then I do a pop. When I do the pop, R15 goes away, and a pop moves the stack pointer again back to where it was. So the push and the pop look like that. The base pointer doesn't move at all. Isn't this fun? And at this point, like I'm just doing work, right? I'm just writing code. I'm moving values around. I'm doing calculations, and so I'm accessing memory. Whatever the function happens to do, whatever this code does, it's doing its thing. At some point, we're going to be ready to exit this function. So the callee is going to exit, and we're going to pop back to the caller. Like, what does that mechanism look like? Well, again, these functions are not connected in any way except through the stack. It's almost like, you know, the old putting a message in a log, you know, as you're walking through the woods for someone else to pick up. You don't know that person or who they are or where they are. You just know you can leave a message for them. Same thing here. I know I can leave a message for the caller. I don't know where the caller happens to be, but I can leave a message for them. And so I'm going to do this. Once everything is done, if there is a return value, I'm going to stick it in RAX. RAX is where the caller expects to see any return values. So just stick the return value into the accumulator. Now I'm gonna just like clean stuff up. I want to, you know, I allocated this space here. I moved RSP up by actually I did it here, right? Right here, I subtracted 20 bytes or 32 bytes rather to give me this space. Well, I'm gonna clean it up. So I'm gonna add that back in. So add back any value that you subtracted from RSP, just to move RSP back to where it originally was, essentially it's going to be pointing back to RBP at that spot. So here we added 20 hex, 4 words, just subtract 4 words, and now RSP is going to be back here. It'll be back there. Next, we're going to pop anything that I pushed. So remember, these registers are fixed on the CPU, right? If I needed to save off a value, I did a push to the stack. Well, it's going to be sitting out on the stack somewhere. I got to pop that back to restore the value in that register. So any of those 7 registers that I'm required to save by the ABI on entrance to a function call, I'm going to pop them back in a reverse order, of course, because they were pushed in. If I pushed ABC, it's going to be pop CBA because they're sitting in reverse order on the stack. And then move the original frame pointer back to where it should have been. That's the loudest that mic has been when it fell. So I need to move the original frame pointer back to the caller's value. You might recall that here, there's the old RBP, right? So what did I do? I cleaned stuff up. I moved this guy. I moved the stack pointer back to here. Now what's sitting at the top of the stack? It's the old RBP value. So all I have to do is pop the stack, and RBP is going to be restored. So now RBP, when I do that pop, it's going to look like this, like that, because that was the old value. So it's going to move back to the original frame on the caller side. And then call return. What return does is return looks here. So I've popped off RBP. Now what's sitting on the top of the stack? The original return address. So what did we do? We did this. We popped RBP. So RBP's value is this. The pop moves the stack pointer. So now the stack pointer is here. The next thing we need is the return address. It's sitting at the top of the stack. All we do is pop it. And where do we pop that return address into? We pop the return address into the program counter, RIP, because the program counter keeps the address of the next instruction to execute. We pop the old return address into the instruction pointer. On the next clock tick, the next machine cycle, it goes and says, oh, now where am I executing? Oh, I'm executing at this address. That address was the return address, which was the next instruction in the caller to execute when we come back from the function. And what's going to happen when we come back from the function call, the result's going to be in the accumulator RAX. Let's put these back to where they were. Let's see, it was RBP was here. Actually, RBP didn't move, it was there. The stack pointer moved, it was up here for that, just for that slide. And call return. And essentially, that's what return does. That return command pops the return address and then sticks it into RIP. That's all it does. That's all it has to do. Oh. Instead of mucking around with one of the earlier ones, I drew a new one for A1. Everybody with me still? It got really quiet out in Zoom land. All right, cool. Let's look at this code. This is the code we looked at earlier. Sam says, yeah. So let's look at this code again. This is the code we looked at earlier on Thursday, I think it was. Let's look and see what it really is doing here, right? All right, so here's test func 1. It's going to set up a variable called 1, and then it's going to pass that variable to test func 2, and it's going to store the return value in this integer called value. This is the code that was generated by the compiler. I probably just did an object dump on this on the object file to grab this. All right, here we go. These first two commands, that's just what the ABI requires, right? We're going to push RBP. We're not actually going to mess with any of the registers, so we don't have to preserve anything except RBP. But there's the push to RBP. That does this there. So we just pushed RBP. So that's the condition now. Next thing, we're going to make RSP, the stack pointer, we're going to make the stack pointer and the base pointer equal to each other. That was that. So RBP equals RSP, that's that line of code. So now we're right back here where we started, right? Now what are we going to do? We're going to give us some space on the stack. So subtract 16 bytes from the stack. That gives us that 16 bytes of space to play with. That moves RSP up a little bit. And now I get 16 bytes to do whatever I want. That was this condition. Should look more like that. We haven't stuck anything in there yet. So that moves the stack pointer up by 16 bytes. Now we're going to start doing stuff. So let's move a 1. $sign means it's a numeric value, a literal value. So let's move a 1 into this location. What location is this? Excuse me. It is whatever RBP is pointing to minus 4. Well, RBP is basically pointing there. And minus 4 is going to be 4 up from that. So we're going to stick a 1 here. Why is it 16 bytes, asked Sergey? I just made up 16. It was just seemed like enough space. I mean, looking at the code, we really just need like 4 bytes, right? So we could have just done 4 bytes. The 16 here was arbitrary. So I move up, yeah, sure. I move a 1 into that stack area, that frame space that I just set up. Now I'm going to take that 1. So I'm going. One question I have is, I don't know why there are 2 move operations here. Actually, 3 moves operations. I don't know why I couldn't have just done it in 1. That's something on my plate to go figure out. But what's happening here is first I move the 1 into the frame, basically putting it here like this. So I'd have 0x1 here. Jonas, I'll get to you in a sec. Then I'm going to move that 1. So I go back out to the frame memory and take the 1, the value there, and stick it in the accumulator, REX. And then I'm going to copy it into RDI. Again, I'm not certain why it's a 3-sequence move here, but I'll find out. Jonas asks, can I explain more time why we need space after the RBP? Yeah, it's just for our own protection. So here's RBP, right? And it used to look like this. So coming into the function, after the first few commands, it looks like this. The problem is that if I'm using the base pointer now to store stuff, let's say, I stick a 20 over here or something, or that 1, 0x1. So here's the 1, and if I stick it here and now do a function call, when I do the function call, one of the first things you do is save RBP off and then set the stack pointer equal to the old RBP, right? So to the top of the, set RBP to the top of the stack. So the new function call, it would look exactly like that going into the function call. I'm going to lose that value. So instead what I do is I give myself some space by moving the stack pointer up. And now when I make a function call from this spot, RBP gets saved, but then RBP gets set equal to RSP, and so they would both point here instead. They would point here. It would look like that. So what I'm doing by making the space on the stack, by subtracting that 16 bytes or 10 or whatever, I'm just giving myself some protected space for if, in the case I do a function call, that stuff will get restored when I pop back out. Z. Sweet. All right, so these 3 lines from here to here, really I'm just setting up the call, right? So I'm taking that 1, and notice where it ends up. After those 3 moves, it ends up in RDI. Why is it in RDI? Let's look back at the AE spec. Here's the calling convention. Where's the first parameter go? RDI. When I'm making a function call, the first parameter gets stuck into RDI. And so that's why that's going into RDI, because I'm about to make a function call. So that ends up with a 1 in RDI. That's essentially setting up for that. Now I'm going to make the call. So call Q, that call is the jump to the new function. Now there's something special about this command. These are all zeros. So that address, typically, those 4 bytes are where I'm going to jump to. However, I don't know where I'm going to jump to. This is not an executable file. This is an object file. The way this was created was I put these 2 functions into a file and then compiled it to an object. I did not link this. There's no executable. It's just an object file, like a library almost. There's nothing to jump to yet. Like, this will be linked in to an executable file at some point. Remember, the linker takes a bunch of object files, links them all together into the executable format. Well, before they're linked, I don't know where those functions are going to live inside the process's memory. Just don't know. And so I can't put an address here. This is a relocation indication that I'm going to relocate this function wherever it happens to be. I need to jump from there, and it'll calculate it at link time for me. So this call, this stuff probably doesn't make sense. It doesn't make sense because we don't know where we're jumping yet until the linking step. But I'm going to make the call right there. So that is this call. Test func 2 passing a 1, that's that call. Let's go look at test func 2. What are we doing? First thing is save RBP and then set the stack pointer to RBP equal to the stack pointer. So that's this situation, right? So I'm basically making a call right here, and then the new function, the guy I just called, the callee, is going to store this. It's going to push that. It's then going to set RSP equal to RBP like this. And now I've got space here. That's the space for the new stack frame that I'm going to create for func2, function 2, whatever I called it. All right, so we save off the base pointer, set the base pointer equal to the stack pointer. And now I'm going to grab that parameter that's in EDI, that's the first input parameter, and I'm going to stick it on the stack right here. So RBP minus 4, it's going to end up, so my scratch guy over here. So if that's the new stack frame, right now they're equal to each other, I think. Bip, bip. So they look like this right now. So I'm just going to move this guy up. I probably should have made some space, huh? Why didn't I make space here? Minus 4 RBP. It seems like we should have made a little bit of space, because now, I mean, I'm not going to do a function call, so I guess I don't have to worry about it. But if I didn't make a function call, RBP plus 4 is right here. It's right here. Copy that. Oops. So that's where that 1 would go, RBP plus 4. And then there's nothing really protecting that. So if I did happen to make a function call right now, I would lose that 1, because RBP and RSP are below it essentially. But nevertheless, we're going to move it into that location. So move the value in EDI into the base pointer minus 4, and now just add 1 to it, because what's the function do? Plus plus whatever the value was. So it's going to add 1 to the value in that memory location. Now I've got a 2 there. Now what? I'm going to return it. So take that 2 and move it to RAX, which is where the return value is supposed to go. And now I'm done. All I have to do is pop the old RBP that resets RBP to the caller's stack frame and then do a return. So on return, RBP gets popped. It's going to be here now. The stack pointer doesn't move because we didn't touch it. And the return value is going to be in RAX. So if we go back to the caller function, here was the original subroutine call. Now we're going to take RAX, which is the return value, and stick it into RBP minus 8. Well, RBP in this case is this guy's. Actually, he's probably here, right? This was RBP. No, that was RBP. So he's going to push it into RBP minus 8. So it's going to go down this direction. Then all we have to do, are we returning anything? No, this is a void function. So I'm not returning anything. Leave. Leave does some cleanup operations for us. Like it moves a couple of internal pointers around and then do a return. And now we're returning back to whoever called test func 1. Why isn't that? I'll have to think about why that didn't, that really should have added some space. NOP, Jonas, NOP is no operation, no op. It's a dummy instruction. It's a short instruction. Sometimes we use it to align things in memory. I have to think about why that didn't move the stack pointer around. All right. Cool, huh? Like you literally can, as I said earlier, like you can just, we haven't really studied the assembly language all that much, but like we can kind of figure out what's going on, right? Once you know a couple of conventions about how to write stuff down, oh, we know push and pop, we know move, we know subtract and add and so on. Like those are just really simple. You literally can just, and the way I write assembly language, like I do the same thing as I do with stacks and so on, like that bubble sort. Oh my God, you should see my whiteboard at home, because I always have to solve the problem too, right? When I'm giving you guys one, I got to solve it too. And so my whiteboard at home is just pointers everywhere, boxes for, oh, this is what the top is, this is what the next thing is. And you just write it all out. Same thing here. Actually, we used to, oh God, this is going way back. We used to have these cool little like mini whiteboards, but they were printed with the registers of the CPU you were working with. Like, an x86 CPU would have the 16 registers and a couple of the important pointers, just boxes. And then you could write in and erase and, draw on those. It was really handy to use to like trace this stuff out. Yeah, Jonas, I think probably, yeah, the compiler knew there wasn't another function call, so it didn't have to protect that space. I think that's probably what happened. So it could have been an optimization. Yeah, I didn't have time in here either. I wanted to also do, we'll have to do it on Thursday, like write a loop so you can see what a loop looks like in assembler, because that's kind of cool too. So again, like the stack frames themselves, they're there because I specified the -G switch in GCC. When I did the compile, I said, hey, I want debug information. The stack frames really are usable for debugging. They kind of get in the way of the running program. It's just extra stuff we have to do. And so if I'm optimizing, or if I don't tell the compiler to add -G stuff, the debug stuff, it's going to skip the stack frames unless it absolutely needs it. And even then, it probably won't use a frame itself. It'll just manipulate the stack pointer. It's still going to use the stack for sure to do pushes and pops, but most of this stuff is going to happen in registers. Well, it's just because they're faster. It's difficult to debug registers because the registers don't have addresses. And so it's really hard to like trace stuff around as we're moving bits around. If they're all in registers, it's hard to see, especially through an IDE. But if it's, it's a stack, those have memory addresses, we can go look at that memory address. It's a little easier, I guess. Speaking of registers, like you can use the registers right from C if you want to. And the poster child for this is a counter in a loop. Like if I go this, if I do this, the variable counter is going to live in the data portion of your program, the process. So it's going to be memory set aside for counter, and then every time I add one to counter, I'm going to have to go through a couple of memory references. So the first reference for counter gets us into the process memory, the location for that variable, but that's a virtual address. It's not a real memory address. And so I've got to go through a translation step to translate the virtual address into a real physical address and then do the operation. We'll look at virtual memory in a lecture or two. It's a lot of work. Like that takes a lot of time, a lot of machine cycles to do that. If instead I can put that value into a register, the register is almost like a one machine cycle operation to increment something or two. It's really, really fast. And to do it, you just put register in front of it. So register int instead of just int will tell the compiler, hey, take this value, stick it in a register and work with it there. It'll speed things up significantly, especially for large loops that just doing a lot of iterations. It's a really nice little optimization for us. There's of course, there's always, but there's always a but to this stuff. But because it's in a register, registers don't have addresses. And so if I can't do this, for example, I can't say, oh, bar is a register integer and then pass its address to something that requests a pointer. I can't because bar doesn't have an address. It lives in a register instead, and there's no way to dereference it. I just can't do that. That's a compiler syntax error. And this stuff, maybe we'll do that. Maybe we'll do that on Thursday. Like write a loop in C, look at and see what it looks like in assembler, but then embed the assembler right in the C code. There's a directive, sort of like #include. It's #ASM for assembly. You can just tell the compiler, hey, the following block is straight up assembly language. Don't compile this, just use the assembler, and it'll do that for you. We used to do that all the time at Fidelity on the trade side, in the retail, which does stock trading and so on. Like most of those systems were written in C, but when we really needed performance, we embedded assembly language in to get the max throughput through those systems. You don't want people, have to wait to do a trade. They get angry. All right, so bottom line, like these stacks are just everywhere in the kernel. We just use stacks constantly. It's a really simple data structure, but it's really useful. They're just everywhere. We've got registers that we can use. Every process, every program has its own values that live in those registers. So for example, if I'm running Keynote right now, if I switched over to WebStorm, so Keynote's register values would have to get saved, all of them. And then, including the program counters and so on, those all get saved off. And then the new values for WebStorm have to get loaded into all those registers. And then we pick up wherever the program counter is pointing. That's called a context switch. And we won't dig too deeply into that because it's more of an operating system thing. But our process will get context switched in and out of the CPU. And we're kind of looking at stuff from the process standpoint. So we'll get into a little bit of context switching a little bit later. And then that idea of using a base pointer and an offset, that's a constant thing we do in assembly especially. We're constantly setting a base pointer and then using an index plus or minus from there, that offset value. That's a really, really common thing to do in assembler. We just do it everywhere. So those things, registers, base pointers with indexes / offsets and so on, and then the stacks themselves. If we look through kernel code, that's about all you're going to see. Everything else is kind of just housekeeping. All right, hey, I got a minute left. Ooh. All right, guys, so that is it for today. On Thursday, I'll remind you about the midterm and sort of go over again what's going to be on it for folks who missed this. And I think on Thursday, we'll kind of stay in this mode. We'll write some C code, examine the assembler for it. We'll do some loops and see what those look like. Maybe some pointer manipulation and see what that looks like. I think it's useful for us to see what the assembler is that's spit out by the compiler. Helps us understand what's happening. All right, that is it. I will see you all on Thursday. Enjoy the beautiful weather. It's gonna be 70 on Thursday here in Boston. Cannot wait. Cannot wait. Bye, guys.